Good morning, friends. I am extremely happy to be here for my course, Aircraft Systems. Today I am in question bank and their answers, and I am in module number 4th. Today's topic is engine control and the fuel system. I am Dr. Dwivedhi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. As of now, I have completed all the 5 modules, followed by problem solving and case study sections of 15 lectures. Then I have completed my definition and terminology 5 lectures, and in question bank and answers I have completed 3 lectures, and today I am in the 4th. It is second last. After this I have one more lecture and then my course will end here. So today's topic is engine control and the fuel system, and in this I have divided this today's lecture in topics and CO mapping zone. Like engine fuel control, it is belongs to CO5. Engine speed control, it is also CO5. Principles of GT engine, it is also CO5. Engine power management system, this is also CO5. So here we can see that before I commence this, all topics I have covered in my module 2 and also in DT section of module 4th. Today the first question, which is discuss about engine and fuel control system in an airplane. So we know that the engine control also comes under the primary flight control system. There are 3 primary flight control systems. This I am going to show here. So what are the 3 primary flight control systems? We know that the aircraft can move in this direction. It is called the longitudinal direction. Aircraft can move in a sidewise. It is called the lateral direction. Aircraft can go up and down also. It is called the vertical motion. In this, they are the linear motion, but in all the 3 axes, that is the longitudinal axis, lateral axis and the vertical axis, there can be a rotation. So these rotations can be obtained by the help of the 3 primary control surfaces. They are elevators, ailerons and the rudder. The first control, which is the elevator, this gives the longitudinal motion, that is the pitching motion of the aircraft. So this motion, the pitching motion like this, is achieved by deflecting the elevator, which is fitted on the horizontal stabilizer. They are the horizontal stabilizer, and this horizontal stabilizers, when you move down, the force will act upward and tail will go like this, nose will go down. So if you want to make nose down, then this elevator has to go down. Same way, if you want to make nose left or the right, that is called yawing. Yawing is achieved by the help of the rudder. This is the rudder here. This you can, if I see, so from here, this is the rudder here. This rudder has to move. If you want to move left, it has to move left like this. If you want to make right, it has to move right like this. So left and the right. And this is achieved, so the force will act in opposite direction of the motion of the rudder. So if you want deflect this side, force will act and nose will go in the same direction of the deflection side. Same way, the aileron can be operated by the help of deflecting the aileron either upward or the downward, and the rolling effect will take place. Now, discuss about engine and the fuel control system in an airplane. So, all modern turbofan engines are controlled by FADEC, that is called Full Authority Digital Under Engine Control System, that is called FADEC system. Despite this fact, large number of older hydromechanical controlled engines are still in use. To give an overview of these kinds of system, they are described as well here. Because these hydromechanical systems, hydroelectrical mechanical systems of engines are already existing, because this FADEC system is introduced very recently. So only the modern latest aircrafts, they are equipped with the FADEC. So we should understand the old version of also this system. So main task of this system is, the main task of the engine and the fuel control system is to metering of the fuel flow to the combustion chamber under the operating condition of steady state, acceleration and the deceleration. So the main objective of this system is to, at any condition, it may be steady state flight or in the high speed accelerated flight or in the slowing down during the landing, deceleration, this should meter the flow of the fuel as per the requirement. The system must achieve this with the aim to keep the engine on the thrust level demanded by the pilot. So at different types of flight phases, the requirement of engine thrust is different. If it is climbing, we need the more thrust. If it is coming from approach, we need very minimum. During the cruise, we need the average type of steady state flight. So steady state acceleration and the deceleration, the system must achieve this with the aim to keep the engine on the thrust level demanded by the pilot. To prevent the exceedance of the operating limits, limiting functions ensure the operating within the limits of the shaft speed. So we have some limiting function and functions, and it will operate in the given speed of the aircraft. Temperature and the pressures, to accomplish this task, the engine control system also control the function of the other engine systems. These systems are known as the engine subsystem for describing of the fuel and the control system. Next question is, explain the speed and the thrust control of any aero engine. So how the speed and the thrust control of the aero engine is achieved. So this I am going to discuss in this question. For the control principle of a turbine engine, the shaft speed and the thrust are the two most important parameters. The simplest control system is a shaft speed control system. As long as the power lever angle is constant, it keeps the shaft speed constant. A typical application for a constant shaft speed control system is the APU. If an aircraft engine is controlled by a shaft speed control system, the thrust will change with changing air density, and the pilot has to readjust the thrust lever to keep the required thrust. So like propeller aircraft, as in when you go in high altitude, the density of the air is reduced. So from the same speed, you cannot get the same thrust, because it is dependent upon the mass of the air. If the density is reduced, the mass is reduced, so you need to operate more throttle. So speed of the propeller will increase, and it is a more quantity of air will be sucked. For the operation of the aircraft engine, a thrust control system is the most suitable. Here the pilot can directly select the thrust needed for a flight maneuver, and the control system keeps this thrust constant. So for the operation of the aircraft engine, a thrust control system is the most suitable. Here the pilot can directly select thrust needed for a flight maneuver, and the control system keeps this thrust constant as per the maneuver. Next question is, infer the engine shaft speed control. So this is another system of which how we can control the speed of the shaft of the engine. So, in a speed control system, the shaft or the rotor speed is the main control parameter. The fuel control unit FCU uses a speed governor to adjust the shaft speed to the value demanded by the input of the power lever. The fuel flow for the acceleration must be between the steady state line and the surge limit. For the deceleration, the fuel flow must be between the steady state line and the flame out limit. So, the fuel flow for the deceleration must be between the steady state line and the surge limit. For the deceleration, the fuel flow must be between the steady state and the flame out limit. So, this you can see here that this line, it is a plot of fuel flow and the idle and the N2 maximum. So, if you increase from here for a steady state, the line is going like this. For the surge limit, the speed is, this fuel flow is high comparing to steady state, and for the flame out means it is going to extinguish, the flame is going to diminish. So, in this case, the fuel flow is reduced. So, here we have three plots. This three plots shows the surge limit, then steady state and the fuel demand, then flame out limit. So, here we have one more term, it is called the compressor stall, and it is also called the surge. It is a much more frequent phenomena than the flame out and may lead to flame out. Surge occurs when engine speed, airflow and fuel supply get out of balance and the required distribution of pressure throughout the engine is disturbed. So, this stall is a much more frequent phenomena than the flame out and maybe lead to flame out. Surge occurs when engine speed or airflow and the fuel supply, these three things get out of balance and the required distribution of the pressure throughout the engine is disturbed. So, this is called the compressor surge or the compressor stall. And what is the flame out? Flame out is the rundown of a jet engine or other turbine engine due to the extinction of the flame in its combustor. So, if the combustor do not get sufficient amount of flame, it will extinguish. So, it will flame out. The burning will stop there. So, it is a rundown on the combustion. This is called the flame out, and these are the two types of phenomena which is shown in this diagram. To adjust the calculated fuel flow to the current air density at the combustor inlet, the fuel control unit needs at least the input of the compressor inlet temperature CIT and the compressor discharge pressure CDT or PS3, additionally to the N2 speed and the power level input. With these inputs, a simple speed control system can operate. To operate as a control unit for a turbine engine, the fuel control unit must have a minimum of the functions. As an example, let us have a closer look at the hydro-mechanical FCU for the operation and speed control device. It needs the following subsection: the fuel metering section, the governing section, the limiting section. So, these are the three subsections are required. Fuel metering means it should measure how much amount of fuel is required. That has to be measured as per the compressor inlet temperature, compressor discharge pressure, N2 speed and the power input. Then governing section, it should govern this, govern the amount of fuel, how much is required for different condition. And there is a limiting section, it should not go above the surge and it should not go below the flame out section. Next, I am going to discuss about demonstrate the gas turbine engine cycle. So how these gas turbines are working and how these cycles are described. So here I am showing the three diagrams here. The first one is a block diagram, second one is a PV diagram, and third one is TS diagram. In this I am going to discuss about first about the demonstration about the block diagram of this. So here we have the three major component of the gas turbine engine. First one is the compressor, second one is the combustion chamber, and third one is the turbine. So here if you see one, the fresh air is entering. So here fresh air is entering here, goes to the compressor, and this you can see the size is reducing. As it is compressing, the size of the compressor is reduced. From here, there are number of compressor. These compressors will be compressing the air, and slowly in a number of stages. Each stage consists of one rotary or rotating parts and another is stationary part. The rotating and stationary combined is called one stage. So in the first stage there are number of stages, and every stage there is some increase in the pressure, and as per the requirement of this combustion chamber pressure, the air is compressed. From here it goes to the combustion chamber. The high pressure and the high temperature gases are entering in the combustion chamber. Here the fuel is mixed and spark is provided for initial, and after that it is running by itself. So here 2 to 3 the fuel is injected and the temperature is increased tremendously in a constant pressure. The pressure will remain constant. So now it reached to the 3. From the 3, the expansion is taking place. Gases, a high temperature and the high pressure gases will expand in the turbine. So this you can see the volume of the turbine from the here initial stage to the last stage. This is volume is increasing. And this is shown here by the 3-4 at a adiabatic process where entropy is constant. So here we reach to 3 to 4, and from again 4 to 1 the energy is out. So this is the block diagram, and same block diagram is shown here in our PV and the TS diagram. So if you see the PV diagram, first is the compression. It is called the compression. I am writing here compression, and here is the combustion, and this is the expansion. In turbine, it is called in turbine, and this is the compressor, and this is the combustion chamber. Okay, so here is a PV diagram, and this you can see here that 1 to 2 pressure is increasing, temperature is also increasing. This you can see in TS 1 to 2. Here 1 to 2 pressure is huge increasing, temperature is not much increasing. But if you see 2 to 3, here the fuel is added, this fuel is burned, and from 2 to 3 a huge amount of temperature is increased. This you can see from here to here, this much increase in the temperature, but pressure will remain constant in the combustion chamber. Now from 3 to 4 it is a constant entropy or the adiabatic process. In that your entropy remain constant. This is the entropy remain constant. 3 to 4 temperature also fall down and expansion is taking place, and the work output is done here. Here Q in and here work out or the Q out. The exhaust is taking place here. So in this way this system is working, and here a gas turbine engine cycles and their operating block diagrams are shown for the references. We should take care of while drawing this 3, 4 and the 1, 2. 3, 4 should be perpendicular to the S line, the horizontal line, and 1, 2 also it is an adiabatic process. This is also adiabatic. This 1, 2, and 3, 4. 1, 2 and 3, 4 both are adiabatic process. That we have to make sure that these things are working as per the requirement. Next question, illustrate about airplane propulsion system. So this already I have discussed in the principle of operation of your gas turbine engine. We can divide this propulsion system into mainly 2 groups. One is the reciprocating engines and another is the rotary engines. So in this reciprocating we have this 2, 3 types, V type, in circular, in the axial. This all configuration are here, and here we have the gas generators, here we have the compressor, combustor and the turbine, and this configuration. So propel means act of propelling, to propel, to move forward. So that is the meaning of the propulsion system. Here it is shown here that we have already explained in my previous lectures. So here we have the jet engine. This is the jet engine. This is the turbojet engine. This is the turbo fan engine. These are the rotary engine, or mostly gas turbine engine we call it. So this jet engine is mostly used for the high speed aircraft, especially for fighter and civil aviation. Now this is the turbojet. In this it is not, it is a turboprop, sorry. This is the turboprop and this is the turbojet. Okay, so this turboprops engines are used. In this, a propeller is used. This propeller is driven by this turbine and it is sucking the air from this side, and this aircraft will move in this direction, action and the reaction. So this is used for, this type of engine is used for low altitude and low range of the aircraft. It is much better than the turbojet engine. But nowadays we use the turbofan engine. In this turbofan, this you can see there is a fan ahead of the compressor, and here a huge amount of air is bypassed from here and here. This is the bypassed air, and some amount is entering in the core of the engine. It is a compressor, and here we have the spooling, the low pressure compressor, and this is the high pressure compressor. Here also it is HP turbine, and this is the LP turbine. So LP is connected with LP and HP is connected to the HP. So these are the systems, and running, this is shown here, and this you can see that air is entering from this side, and then this is the fan here. In the fan, a huge amount of air is bypassed. It is not taking part in the combustion, and mostly 50%, and the remaining is entering here, and then this goes to the combustion process here. In the combustion, the only out of 50, only 20 to 25% is taking part in the burning. Then remaining is used for the cooling, and then it goes to the turbine here. These are the turbines, and from here it exhaust goes to a nozzle, and these nozzles are providing the thrust for the aircraft. So next is explain the principle of operation of aircraft gas turbine engine. How jet engine works. Jet engine move the airplane forward with a great force that is produced by a tremendous thrust and causes the plane to fly very fast. all jet engines, which are also called the gas turbines, work on the same principle. The engine suck air in at the front with a fan. A compressor raises the pressure of the air. The compressor is made with many blades attached to the shaft. The blades spin at high speed and compress or squeeze the air. The compressed air is then sprayed with fuel and an electric spark light the mixture. So, I think it is, so what we have to do is, first we have to compress. This compressed air is going to the combustion chamber where fuel is sprayed and spark is given. Then it is burning there, and this high temperature and the high pressure, this goes to the turbine. In turbine, gas expands and work is done. This work is transferred to propeller or nozzle as per the requirement. So this is a basic principle of gas turbine engine. The burning gases expands and blast out through the nozzle at the back of the engine. As the jet of the gas shoot backward, the engine and the aircraft are thrust forward. As the hot air is going to the nozzle, it passes through another group of blades called the turbine. The turbine is attached to the same shaft as the compressor. Spinning the turbine causes the compressor to spin. The engine shows how the air flow through the engine. The air goes through the core of the engine as well as around the core. This causes some of the air to be very hot and some to be cooler. The cooler air is then mixed with the hot air at the engine exit. So here it is shown a flow diagram, a air flow diagram. How this air is going. So just I am going to explain here. The air is entering from the inlet here. This is the inlet, goes to the compressor. These are the compressor here. Here is the combustion chamber. These are the turbine. This is the nozzle here. So the air is entering here, going to the compressor. Here it is compressed up to here. Then it goes, it is the HP, and then one part of it is going from outside. Another, it is going in the core here. This core air is compressed again with the high pressure, and this goes to the here combustion chamber. Here the fuel is sprayed and spark is provided. This high temperature and the high pressure air is increased. This goes to here the turbines. In the turbine, the temperature is increased, and in the high temperature, the temperature is reduced, pressure is also reduced, and expansion is taking place, and the work is done. So this is the principle of gas turbine engine. Next, I am going to discuss about engine thrust control. For thrust control, the control system uses a main control parameter. So how we can control the thrust? So we have to use a main control parameter which is directly related to the thrust of the engine. This parameter can be the N1 speed or the engine pressure ratio EPR. So two things are there. Either you take the rotation of the engine, or you can see the engine pressure ratio, how much pressure is increased. Which of the two is used depend upon the philosophy of the engine maker. Like GE aero engines and CFM use the N1 speed. However, the Rolls-Royce and the Pratt and Whitney, they use the EPR, engine pressure ratio, for this purpose. So if the N1 is main control parameter, the control system keeps the airflow through the engine constant by adapting the N1 speed to the changing density of the ambient air. For this purpose, it must receive the information about the air density from the fan inlet. So it should, if it is the N1 rotation of this thing, so how much air is coming? So density of this thing has to be calculated by the help of inside the inlet before the fan. So here this, we can see here that N1, okay, this is the fan here. So, and here is the speed of the engine. So this is the N1, and this is the high pressure is N2. So in the first case, we assume the N1. So here we have to sense the density, because if the density is reduced, the thrust will also reduce. So here low pressure compressor. All this blue color is a low pressure zone. Red is high pressure compressor here. This one. Yellow is a combustor here. This is the combustor here. And this is the high pressure turbine. This one is the HP turbine. And the green is the low pressure turbine. So this N1, N2 is on. So this is the high pressure zone RPM, and this is the low pressure zone RPM. This is the N1 and N2. Next is the illustrate the power management control system, how the power is managed in different types of flight condition, different types of engine load situation. The inputs necessary for this density correction are the pressure and the temperature from the fan inlet. So density correction we have to see, and this we can get from the pressure and the temperature from the fan inlet. This you can see here, P and T at this inlet, we have to see it. This unit is an N2 control unit because the N2 is the only shaft speed information for this control unit. The matching between the two shaft speeds changes with the deterioration of the engine, and the actual N1 speed will always be few percentage below or above the correct N1 for a thrust setting if the control unit controls the N2 only. For the precise control of the thrust, it is necessary to control the fan rotor speed N1 precisely at the correct value for the demand thrust. Control system with hydromechanical fuel control units use electronic supervisory control unit as an N1 controller additionally to the N2 controller FCU to solve this problem. Such a supervisory control unit, for example, is the power management control of the CF1680C2 PMC version of the CFM 56-3 engine. So this power management, here we do both N1 and N2, because N1 after sometimes there will be a sluggish operation of the engine if the engine is getting little older. So we have to monitor N1 and N2 both, and this type of system is modern aircraft engines like CFM engines we use and we control, and here we use the power management system in this type of system. Now FCU. Describe the fuel control unit. A very important unit. So this is the input for a FCU. Input for a FCU with thrust control capability for a twin spool engine. So here this, if the control system uses the EPR, engine pressure ratio, as the main control parameter, it keeps the thrust constant by holding the EPR constant. Thus, it also keeps the airflow of the engine constant. the N2 controlling FCU is overridden by the EPR controlling electronic supervisory control unit. This EPR control principle is used in the version of JT9D-7R4 and the RB211-524 engines. So here this you can see here that in this diagram we have to see that N2 RPM, PS3 pressure, temperature, CBP, VBV feedback, VSV feedback, fuel to the engine. All things are coming to computing section. Here we have the thrust lever, it will be operated, start lever is operated, fuel is entering, and here metering, and it will go here as per given from the engine. This T20, PS12, as per these parameters, this will measure and it will give to the metering devices. So this is called a fuel control unit. As per the given parameters, main parameters N2 and the PS3, these are the main parameters, and here T12 at the initial stages, here it will be given at the inlet, and T20 also it is at the inlet, that is near the fan. Temperature and the pressure near the fan. N2 is at the high pressure zone in the turbine, and PS3 also in that, and here we will get the feedback, and accordingly this will be given. Fixed relation between the thrust lever angle and the demand thrust exists as shown in the figure. For a specific thrust, the pilot always select the same TLA, thrust lever angle. Because the control system cannot control the thrust directly, the supervisory control unit calculates the value of the main control parameter N1 or EPR in relation to the demanded thrust. This is done in consideration of the actual atmospheric conditions. The result of this calculation is called the N1 command or EPR command. For this calculation, function of the term power management is used. So here the power management is used here. This you can see the relation between the thrust lever angle and the demand thrust. So here we have the minus 30, here is the 0, and here the plus 30. So it is for the thrust reversal. It is going like this, 0, and as you increase the forward thrust, it is also increasing. Maximum takeoff is here in this. Here we have the power management control system. Here is a TLA, N1, and the final fan inlet temperature, T0. This goes to the speed fuel control unit, speed trim signal. So this is a small diagram is shown here. Here this unit is called the power management control. The power management control compares the actual N1 to the N1 command. If there is a difference, the PMC overrides the speed control of the FCU. To do this, it changes the N2 speed until the actual N1 speed equals the N1 command. In an EPR related system, the supervisory control unit operates similarly but compares the actual EPR to the EPR command. These thrust control systems were the last designed using hydromechanical control system. Engine developed later use pure electronic control system because the digital computer is the only control unit and it has the full authority over the engine control. These systems are called full authority digital engine control system. So this nowadays it is developed and this is used for all modern full authority. Everything is done by this system. So the evaluation of the engine control system. So here I have shown from old to the new. So here the first one is the hydro-mechanical control system. Here the mechanical or hydro and this electrical. So if you see here, this all dotted line is a mechanical or the hydraulic, and the firm line it goes to the electrical signal. So here only hydro and mechanical is there in this. In this case, it is semi-electronic control unit. In this also, if you see here, supervisory control unit is here. It is not in this. This one is new one here. And this is operated by engine sensors. Here we have the aircraft sensors, here engine sensors, and this is electrical signals are coming. Here TLA, it is mechanical feedback, the throttle lever control angle. Here is engine systems. Here we have the engine systems here. Here the flight management systems are here, fuel to the engine. And next, it is a FIDEC system here. It is a modern latest system here. Here we have the engine electronic unit is here. Here TLA, aircraft sensors, engine sensors, all are here. This is also fitted here. Here we have the hydraulic mechanical unit. So this will supply this servo valves. It will open it, then it will go to the flight management valves, and this is the principle of the FIDEC. So now in this way, we are here now. All modern aircraft will use the FIDEC system. Explain the hydromechanical control system. So here I have given all the abbreviation. MEC means main engine control, PMC means power management control, CDP or PS3, CIT is compressor inlet temperature, VBV variable bleed valve, VSV is variable stator vane, PS12 and T0 from the fan, this fan inlet. So these are the things which, so here you can see the PMC here, power management control. Here we have the thrust lever angle, start lever angle, ground idling switch, it goes to MEC. This MEC will take T20, PS12, N2, PS3, T25, CBT, VBV feedback and VSV feedback. VBV is variable bleed valve and the VSV is variable stator vane. So this all inputs are given from here, and inside this is the engine, and here this is the block diagram of CFM 56-3 engine. It is a turbofan engine and very much used in different types of aircraft. So here my references are Moir and the Seabridge, aircraft systems, mechanical, electrical and avionics systems. Then Moir and the Seabridge, design and development of aircraft systems and introduction, AIA education series, AIA 2004. Any questions you are welcome to ask, and my email is ydwivedi@gmail.com, and also I request to like and subscribe this channel, and any query you can make in the comment section or in this email. Thank you very much for joining my lecture, and my last lecture is left. Please do join my last lecture. Thank you very much for this.
Like, share and subscribe. Hit the bell icon for more updates.